All right, this is the AP Physics 1 equation speed review for 2024. This is everything that you need to know to get a 5. I've already actually made a speed review video, but this one's going to be specifically for the equations. The other one I'll have linked in the description if you haven't already seen that one. All right, so this video is going to be broken down into 2 parts. I'm going to try to make this as quick as possible. So the first part is going to be the College Board base equation sheet that they give you. I'm going to kind of just go over that, share some tips with you guys, as well as what each formula is basically for and where to use it. And then I'm also going to give you some dark mode versions of the same exact formula sheet that's really more condensed and concise and really only includes the things that you need to know. And then on top of that, I have 25 derived equations. So, equation derivation is pretty much this whole exam. And so I have 25 common ones, common situations. And so I think that'll be really, really useful. However, that's a 40-minute long video, and I don't want to put all of that into this video, so I've only included a short preview of that. I'll have a way for you to watch the full thing that I'll share with you in just a second. Here are some actionable steps that you can take. As you watch this video, make a note of any equation that really doesn't look too familiar, so that way you can go back to it later. Pause the video before I explain each equation and see if you can understand it before I explain it. And then, of course, after watching the video, just get some practice in deriving as many equations as possible. You can go ahead and download these equation sheets I mentioned. These are just a quick preview of what I was basically saying. So here's the first one. Here's the second one. This was the same exact thing, but it's more condensed. And then this is the derived formula sheet here. And so I made a few mistakes actually as I was doing this. So I have the final corrected version on my website that you can go ahead and download again for free. If you want, you can also pay just a little bit of money. It's very, very cheap to watch the full 40-minute explanation video of all the derived equations. Again, I'm going to include a little bit of a snippet / preview of that in this video. So that way you can get a few of these explanations in. But again, the full video will be linked on my website. And again, I'll have a link in the description to that. Before we get started, who am I? My name is Jason. I'm the creator of nerdnotes.com, where you can find free resources. There's UBQ that has tons of AP style physics questions. It's the ultimate bank of questions. And I'll also have a link to full speed reviews in the description if you need that. I've basically built programs to help people score 5, and that's really where all this knowledge is coming from. I'm condensing it down into very, very short, concise videos to hopefully help you score a 5. All right, let's get started with the first part. So this is going to be the College Board equation sheet, which happens to be very redundant. There's a lot of older, non-tested materials on it, and I'm going to make a kind of just a disclaimer here. Almost all of these equations are kind of useless by themselves. And so most of all the questions that you're going to be answering / doing on the FRQs, and even also the multiple choice questions, are going to be based off derived equations. So taking one or more equations, so actually I should say 2 or more equations, and putting them together and then using that formula to actually solve a problem. And so let's go and take a look at the equation sheet. The first thing is actually just a table of information. The only thing you really need to know out of all of these is just these 2 right here. Acceleration due to gravity at Earth's surface is 9.81. Everyone knows that. And you should also know the fact that as you leave the Earth's surface, so as you get further and further away from Earth, gravity is obviously going to diminish and fade away to 0. Okay, so a way you can actually figure out the gravitational field, I'm actually going to do a quick derivation here just to show you what a typical derivation would be, is I'm going to use this gravitational constant and the FG formula, so for the force of gravity between any 2 objects. And I'm going to say M1G, this is the force of gravity, is equal to the force of gravity formula. So G M1, the mass of the planet that you're on, so if you're on Earth, you would put Earth. I'm just going to put MP for mass of planet, divided by the radius or the distance between the 2 objects. Notice how the mass of the object cancels out, and you're left with the gravitational field, which is equal to G, mass of the planet divided by the radius squared. And so this is the final equation for, again, the gravitational field of any planet, or again, I guess I should say any distance away from that planet. And if you just rearrange this to be r squared times g is equal to GMP, you'll see that we can prove easily that as you increase the radius, in other words, as you get further and further away from the center of the planet, your gravitational field will continue to decrease. And so this is, again, something that they might ask you to derive and do on the test. Okay, so let's go ahead and actually move on to the actual equation sheets now. And actually, one thing before I even move on to that, this table is so underrated. What you'll notice is that a lot of the, not a lot, actually, I think all of them involve these angles. So College Board will only really use strictly these angles. So that way you can actually avoid using a calculator. You can always refer back to this equation sheet. So now I'm not saying to continuously flip back to this equation sheet, but if you do have some of these values memorized, it does kind of make solving problems a lot faster in my opinion. And of course, if you're given anything prefixes and you forget the prefix, you can obviously just refer back to this. One thing I do want to mention is that joules is energy and watts is energy per unit of time, and this is what we call power. So it's energy divided by time. Okay, I think that's it for that one. You can really ignore pretty much everything else. So ohm, volts, all that kind of stuff. Kelvin, hertz is obviously frequency. Ampere, you don't need to know all that. So yeah, I'm not too sure why they even include all this stuff, to be honest with you. It's just old material, really. Okay, let's move on to the AP Physics 1 equations. And the first thing I want you sort of see here is this equation right here, F equals ma. I have no idea why they try to make it look so complicated. It really just is Newton's second law. It's the net force that's equal to the mass times acceleration. Now, it is important that it is important to say the net force, but you don't have to write it in this format. Okay, now before we actually jump into the dynamics portion of this, let's just cover the kinematic stuff. So they're giving you 3 kinematic equations. On my formula sheet, I have 5, and the reason I have 5 is because when I teach this stuff, I usually teach it in the format of like every equation is missing one variable. So for example, this first equation is missing delta x, right? This second equation is missing final speed. And so each equation is missing one variable, one kinematic variable that is, and so my equation sheet will have all of them. So yeah, these are pretty standard. The only thing I have to say about this is that sometimes, and again, I don't know, they kind of flip-flop back and forth here between using this symbol delta and x final minus x initial. So if I just take this here, and if I move x naught to the other side, right, this is really just a fancy way of saying delta x, right? So every place where you see x final minus x initial, you can just replace that with delta x. So that's what I have on my equation sheet if you're confused by the difference. Here they're using delta, they're not really using t final minus t initial. Okay, so for force of friction, this is kind of I guess confusing for a lot of people. All this really means, I've explained this in my other review video, so if you want, you can go check my full explanation video out for this one. But basically, friction has a maximum value. So this usually refers to static friction. And so static friction can essentially have a maximum value, but you don't need all of that static friction to hold something in place. So that's why it can be less than or equal to the maximum value of static friction. And by the way, this is going to be normal force. So when they say Fn, that's normal force, not net force. And so it's going to be the coefficient of friction, which is going to be either kinetic or static, multiplied by the normal force. Now, if something is on a flat surface, the normal force is simply going to be equal to the weight. And if something is on an incline, then the normal force is going to be equal to, of course, mg cosine of theta. So this is going to be your angle. This is your angle here. And so therefore, your normal force, this component right here, or I should say this vector here, is equal to this component of your weight, mg. And so that's going to be your mg cosine component of that. So again, friction on an incline will be mu mg cosine of theta. Okay, moving on. So let me go ahead and erase all of that stuff. Okay, so the second dynamics formula that they give you is going to be force centripetal acceleration. So this is going to be basically your inward acceleration into any arc or circle. And so again, just as a reminder, anytime you have anything moving in a circle, you're going to have an acceleration that always points inwards. And so that's what we call our centripetal acceleration. There's really 3 types of acceleration you should learn about. There's the centripetal acceleration that again points into any arc. There's going to be your linear acceleration that of course causes a linear force, or a linear net force, I should say. And then there's going to be, of course, your angular acceleration, your alpha value that's caused by a torque. And so we'll talk a little bit more about this in a second. And so what I can do here is I can also use my F net equation. So I can say F net is equal to m, and instead of putting linear acceleration, I can put centripetal acceleration. So that's another place where you can use this AC value. So again, anything for satellites, roller coasters, really anything moving in a circle, you're going to be using centripetal acceleration. P is going to be momentum. This is linear momentum. And this is actually another thing I should mention. They're kind of doing all the linear stuff first. And on my equation sheet, I've basically organized it such that I actually give you the rotational motion conversions first. And then I basically just mix all the linear stuff with the rotational stuff by unit. So basically all the kinematic stuff, whether it's linear or rotational, is in the same section, which I think it makes a little bit more sense to do that, because when it comes to finding, for example, the kinematic equations for the rotational stuff, all you do is you take for example, this one right here. Let me highlight this. Okay, so this equation right here is essentially analogous to this equation, and all you really do is you take each variable and you swap out the linear variable for the rotational variable. So instead of putting v final, you put omega final. Instead of v naught, you put omega naught. Instead of linear acceleration, you put angular acceleration. Okay, so that's why I've kind of grouped them together, whereas the College Board kind of does the opposite approach of essentially grouping them separately. So as you can see here, they kind of redo some of the kinematic equations. So it's almost kind of like a redundant thing, as if already given you the kinematic equations here. And so to get your rotational kinematic equations, again, you just got to swap out the variables, really. Okay, so kind of going back to what I was saying earlier, this is linear momentum. Angular momentum is going to be L is equal to I omega. So again, I'm swapping out velocity for omega. I'm swapping out the mass for rotational. So mass, I should mention, is just inertia. That's what Newton said in his first law. An object in motion stays in motion because of its inertia. It's the law of inertia. So the bigger the mass, the bigger the inertia, or the bigger the resistance to a change in its motion. And so rotational inertia is basically the same exact thing. It's a resistance to a change in rotation, basically, rather than translational speed. And so these are actually pretty self-explanatory. One thing I would want to just say here is that, let's just say you have a point mass, right? Well, I have a point mass is mr squared. This is, I think, something that you should actually know that they don't really give you on this equation sheet, but you should know that the moment of inertia of a point mass is mr squared. And then the other thing I can do is I can convert omega into a linear speed by simply doing v is equal to omega r. So I can use these conversions, these linear to rotational conversions that, again, I have on my formula sheet that they don't really give you, I believe. So that's going to be these conversions right here. So kind of going back to what I was saying, I'm going to go ahead and replace omega with v over r. So I'm going to solve this equation for omega and plug in v over r right here. So now I essentially have this other equation for angular momentum, and so that's going to be mrv. Okay, so now this equation is actually pretty helpful. It comes up at least once or twice on your AP exam, so just be familiar with that. Okay, so moving on to impulse now. Impulse is just a fancy way of saying a change in momentum, okay? This is essentially when there is a net external force being applied. So when you have a external force multiplied by a change in time, you're going to get an impulse. And so again, I already covered this in my previous speed review as to how to apply this, but essentially you can also, kind of expand out this equation to m delta v, right? So again, a change in momentum is just simply going to be a change in its velocity. You can also expand this out even further and just say mv final minus v initial. Okay, moving on to the energies now. Now, before I actually cover each type of energy, I should mention that I think one thing that they didn't write down that they really should is EI is equal to EF. This is the conservation of energy. This principle comes up a lot on your AP exam. So if you actually look at the breakdown of topics as to what they test you on for the FRQ section at least, you'll see that energy comes up a lot. And this concept, you almost always get 1 point just for writing that down. Now, these are just types of energies, and all the conservation of energy principle says is that energy is always conserved, and it's only the types of energy that actually transform. So the total energy always remains the same, but it's always going to be converting from maybe kinetic to potential to heat to whatever the other types of energies might be existing in the system. So yeah, this is kinetic energy. Kinetic energy applies to anything that has velocity. This is going to be a change in energy, or even it could be a change in kinetic energy as well. And that's going to be essentially work. So anytime, to think about it this way, if you have a change in kinetic energy, that means you have a change in velocity. Well, a change in velocity implies an acceleration, and the only way you can have that is if you're applying a force. And well, work is a force over an applied distance. And so therefore, again, if you're having a change in energy or even kinetic energy, you're going to be essentially giving it work or converting some of that into work or something along those lines. The important thing to note is that F and D, this is a dot product, which essentially just means that they have to be parallel. And so if you have something like a satellite, so let's just say this is the Earth, and there's a satellite orbiting the Earth. okay, that satellite is doing zero work. Okay, why? Because it does in fact have an inwards force Fg, but it's moving perpendicular. The displacement is perpendicular to the actual force that is being applied. In fact, actually, if it makes one full rotation, the displacement is zero. So that's another way to look at it. And the last way to look at it is that a satellite in circular motion is moving at constant speed. And so therefore, if it's not changing speed, there's no change in kinetic energy. And if there's no change in kinetic energy, there's no work being done. Okay, so there's a plethora of ways that you can look at this. And again, the main point I'm just trying to make here is that the force and the distance it travels have to be parallel to each other. So, if it looks something like this, you're really only going to use in this case, the cosine component of this. So F cosine theta, because that's what's parallel to the distance being traveled. Let's move on to power now. And by the way, I probably should mention that they really should be grouping these together a little better. So they have, again, kinetic energy. This is translational. And then they also have, I should just skip over here and just say it right now. This is kinetic energy rotational, right? So this is KER. And it's basically the same exact equation. You're just swapping out the mass with I, the rotational inertia, and velocity with angular velocity. So that's going to be rotational kinetic energy. And then, of course, you have just your regular potential energies. And so your potential energy due to gravity, essentially, due to height, is going to be mgh. I'm just going to write that down here, mgh. And then your potential energy due to a spring that we also call elastic energy is going to be 1/2 kx squared. So it's going to be right here. So US, they use U for potential. It's going to be 1/2 kx squared. Again, this is for a spring. Now, they also have this other UG equation. Most teachers actually don't cover this, but this is essentially the potential energy, kind of like mgh, except this is for when you're far away from the planet Earth. So this is kind of like the derivation that we did earlier. What is the gravitational force when you're far away from Earth? Well, again, that's something you got to calculate. And so instead of having to calculate that separately, then plugging it into mgh, what you can do is you can just use this equation right here, which just says that the gravitational constant multiplied by the two masses divided by the distance between them is equal to the potential energy. And if you're wondering about this negative sign, it's a little bit hard to explain in the context of AP Physics 1 because you guys haven't done calculus-based derivations yet. And so it does make a whole lot more sense whenever you do the calculus-based derivation. But for right now, just assume that it basically means a loss in energy. So that's usually what the negative sign means when it comes to energy, because energy is a scalar. It's not a vector. It doesn't have any direction. So then negative or positive signs represent either a gain or loss in energy. Moving on to the next few equations. So we're kind of done with energy. They're revisiting kinematics rotationally. We've already covered that. This, again, is going to be just your Newton's second law, except this time it's going to be torque is equal to IA, or I alpha, I should say, rather than F is equal to MA. Okay, so those two equations are analogous to each other. They then go on to give another equation for tau, or the torque, which is R times the perpendicular component of force, which just is R F sine theta. We've also already covered that. That's going to be your angular momentum. And this is going to be your angular impulse. So linear impulse was just, again, delta P, which is force times time. And over here, they swapped out force with rotational force, which is tau, or torque. Okay, here's another force that you should be aware of, and that's going to be the force of a spring. This is what we call Hooke's law. And all this law says is basically the more you stretch out a spring, the more the force is going to exert in the opposite direction. So typically they have a negative sign here to indicate that it's a restoring force. But again, the negative doesn't really matter too much. It just tells you that it's a restoring force. We've already covered this. Again, this is your potential energy due to your height, just mgh. You have your last few equations that are going to be for your last unit, simple harmonic motion. So period is going to be 2 pi over omega, or 1 over f. I just want to quickly clarify this. Period is how long it takes for you to travel in a circle. And so if you think about it, your distance that you travel in a circle is just 2 pi, and this is 2 pi radians, of course. And the time it takes is, of course, what we call your period. And so again, your radial distance divided by your period, how long it takes, is omega. Right? That's your angular speed. And so if you just rearrange that and solve for period, that's going to be period is equal to 2 pi over omega. And so that's where they got that equation from. And then once again, you can also just quickly swap out period for 1 over f. So period is just simply the inverse of frequency and vice versa. And so what you can do is you can actually just plug this equation into this right here and then solve an equation for frequency. And so, what that might look like is, let's actually do it right here. So 1 over f is equal to 2 pi omega. And I'm going to go ahead and solve for omega. So omega is going to be equal to 2 pi f. And so you'll see this equation sometimes does pop up. As you can see, they're actually using it in this equation right here. So instead of saying 2 pi f, you can just replace this whole thing with omega. So this will be a cosine omega t, which again, this is something that you probably won't see on your exam, but it's just worth noting how they get to that equation. Okay, and then this is going to be, the last two equations is going to be the period of a spring and then the period of a pendulum. And so these two things are really, they almost look identical. The way I like to memorize this is that the constants go on the bottom. So the K constant is the spring constant, of course, and then G is just gravity, the gravitational field on any planet, really. Two things to notice, though. The period of a spring doesn't actually depend on how far you stretch it, right? So it doesn't depend on X. So that's an interesting observation. And the period of a pendulum doesn't depend on how far back you pull it, nor does it depend on the mass of the pendulum. So this means it could be like a wrecking ball that's pulled to like, I don't know, like 20 meters above the top of a building maybe, or it could be just like a similar pendulum of a same exact length, and they're going to have the same exact period, which again, I think that's a pretty interesting conclusion that you can come up with just looking at these equations. This equation, of course, is just the force of gravity between two objects. This is something that we've already covered. All right, so hopefully that was helpful. These last few equations, honestly, I'm not even going to cover. These are just math equations. I don't think that this is something that will come up super often. I know volume of a sphere might come up because density is usually something that they and every now and then throw in there. And just remember, density is this value that we call rho, and density is just really mass over volume. And so if we're talking about, for example, the density of Earth, it's going to be mass of Earth over the volume of Earth, which then you can, again, apply the formula for the volume of anything, really. So 4/3 pi r cubed. Okay, with that being said, let's wrap this up now. Let's go into part 2, the derived equations. Now, this is going to be like basically 90% of your tests, if not more. And again, this is not just manipulating formulas. So not just basically taking the equation for kinetic energy and solving it for velocity, right? That's not what I mean by deriving equations. What I mean by deriving is that you're going to take multiple equations and multiple concepts and put them together and connect them like Legos to actually build something meaningful. Okay, so what I would recommend is to kind of just go through each unit and look for these common scenarios where you kind of have to commonly make equations for and practice deriving equations for each of them. And again, I'll have a full video linked in the description below that basically covers every single one of these derived equations that I have on the formula sheet. So that way you can have a proper understanding of all of them and how to actually put them together and what concepts I use to put them together. This next clip is basically just going to be a short clip of a part of that video. So it's only going to be, again, just the first 5 to 6 equations maybe that I cover. And so yeah, hopefully it helps out. Alrighty, let's go and cover these 25 derived equations, starting with rotational motion. I know it's a weird place to start, but it will make sense as I go through the list of derived equations. So as you can see, this equation has x mr squared. So if you've been doing this for a while, you know that the inertia, the moment of inertia of a point mass is just mr squared. The moment of inertia of a sphere, for example, is 2/5 mr squared, and so on and so forth. And what you'll notice is that it follows this pattern of mr squared preceded by some coefficient. So in this case, there's a coefficient of 1. And so what I'm doing is I'm extracting that coefficient and making it into a variable, x. And so I'm going to be using this further down the line, and it will make more sense. But for right now, the general equation for rotational inertia, for the most part, is going to be x mr squared, where x is the coefficient of rotational inertia, as I call it. So it's 1 for a wheel, a thin ring, or point mass. It's going to be 2/5 for a disc or cylinder. It's going to be half for it's going to be half for a disc or cylinder, and it's going to be 2/5 for a sphere. And if it's a rod that's spun from the center, it's going to be 1/3, and if it's a rod that's spun from the end, it's going to be 1/12. You don't have to memorize them, but for the sake of this derived formula sheet, again, I am making that into a derived formula. Okay, moving on to kinematics. So there's going to be about 4 formulas here that we need to get through. The first one is going to be the time taken for a projectile to hit the ground, assuming 0 vertical velocity. So first of all, what does that constraint mean? Well, 0 zero vertical velocity is going to be something that's either launched from a cliff or some height. And so all that velocity is really going to be horizontal, and v naught y is going to be 0. Or something that you're simply dropping. So maybe you're dropping a rock off a cliff. And so in these two cases, the vertical velocity is 0. So given that, we can also say that my acceleration, which is going to be due to gravity, is going to be pointing in the same direction as it's falling. And my displacement is going to be what I call my height, right? So it's going to be the distance it's fallen. And the time it takes is going to be t. And so once I have these three variables, we can just use a kinematic equation that doesn't involve v final, okay? So that's how I usually pick my kinematic equations. I look at what I don't even care about. And so in this case, v final is the thing I don't care about. I'm going to go to my base formulas. And so again, you're going to be given this in your formula sheet, not this one specifically. You're going to be given College Boards, but I'm going to be using mine because mine is, I think, a little bit more organized. And so I'm going to be looking for the one that's missing v final. And so that's going to be this equation right here. It's going to be delta x is v naught t plus half at squared. So I'm going to go back here and I'm going to write that equation down. Delta x, and instead of putting x, I'm going to put delta y, is equal to v naught yt plus 1/2 at squared. I'm going to notice that my initial speed vertically is going to be 0. I'm solving for t in this case. And so if I just rearrange everything and plug in height for delta y, so it's going to be 2h over acceleration, which is just g, is equal to t squared. And then I'm just going to solve for t. So t is going to be root 2h over g. Okay, so that's the first one. Let's move on to the second one. This is going to be the time a projectile is in air, assuming the vertical displacement is 0. So what does that mean? Well, in order for vertical displacement to be 0, let's go and get rid of all this stuff here. In order for vertical displacement to be 0, that means it must start and land at the same height. Okay, and so in this case, delta y is 0. And if I'm finding the time, I should also maybe write down two more variables. And so I'm going to use maybe my vertical speed in this case. And so if my total speed, let's draw that like this, is v naught, my vertical speed is going to be this component right here, which is v naught sine of theta. Okay, so I'm going to highlight that right here. It's going to be this component. That's my vertical component. So that's my initial vertical speed. Let's go and write that down. So v naught y is v naught sine of theta. If you're wondering why I'm doing everything vertically, is because when you're working with something in the vertical direction, you want to work with everything in the vertical direction. So you want to split everything up into x and y components. And so in this case, because I'm dealing with delta y and v naught y, time is directionless. So time doesn't really have a direction. But I'm also going to be working with acceleration in the y direction. So that means in the y direction, it's going to be acceleration due to gravity that's slowing this thing down on the way up. And that's going to be pointing opposite to my v naught sine theta. And so if I said v naught sine theta was positive, or at least I'm implying it's positive, gravity points down, which would be then the negative direction. So acceleration would then be negative g. Okay, cool. I have three things. Now I can pick an equation that will fit them all. And so once again, I'm going to be using the equation without v final because I'm not using v final here. And so that equation, as you can maybe recall, is going to be delta y is v naught yt plus 1/2 at squared. Okay, once again, I'm going to quickly solve for time, and this time delta y is 0. I'm going to move v naught yt to the other side, so that's going to be negative v naught yt, half at squared. One of the time variables is going to cancel out, so it would be negative 2 v naught y all over acceleration. And now I can go ahead and plug in all my variables. So it's going to be negative 2, instead of v naught y, I'm going to put v naught sine of theta, all over gravity, which is negative, and so the negatives will actually cancel out. And so again, this is your final equation for time. Okay, so that's our second derived formula, 2 v naught sine theta over g. We can do the third one. This is going to be the formula for the range of a projectile. Again, once again, assuming 0 vertical displacement, so which means the same thing as it meant in the last problem. It just means that it's landing back at the same height. So when we're dealing with range, that's going to be delta x. So remember what I said. If we're dealing with the x stuff, all my other variables are going to be in the x2. So time is actually going to be the same. So I'm just going to leave time like that. And I just found that over here actually. So we can use the same equation for time as we did in the last equation, because again, time is directionless. However, this time we're going to be using v naught x instead of v naught y, which is again this component right here, right? So that's going to be v naught cosine theta. I'm going to write that down here, v naught cosine of theta. And then we have acceleration, that's going to be 0. And because there's nothing accelerating it horizontally, which is why the speed stays the same in the horizontal direction. So we have 1, 2, 3 things. And so that's enough variables to use in a kinematic equation. So let's go ahead and pick a kinematic equation. That's going to be, again, the one without v final. So this same exact one. Delta x is equal to v naught xt plus 1/2 at squared. And again, because there's no acceleration, that whole thing cancels out, leaving us with this equation right here. Hence why on the derived formula sheet, I put v naught x times t. We know that v naught x is simply v naught cosine theta. And we know that time is what we found earlier here. It's the total time that it's traveling for. And that's going to be 2 v naught sine theta all over g. Okay, this is a multiplication symbol right here, so times. Okay, cool. And now if you want, you can go and further simplify that. The v naught times v naught is going to be v naught squared. So I'm going to get 2 v naught squared cosine theta sine of theta all over g. And if you want, you can, I believe you can even further condense this down. Cosine times sine times 2, I believe, is a trig function that I think is sine 2 theta. But honestly, this is as far as you really need to go. But let's move on to the last kinematic one, and that's going to be the maximum height of a projectile. So there really are no constraints on this one. This is really just solving for how far up a projectile goes. And so once again, if we have a arrow, it's going to be the maximum height, which is, again, delta y. So I'm going to put height is equal to delta y. We're going to be solving in the y direction. So that means I need my vertical component of speed, which is going to be v naught. So this is v naught. So that would be v naught sine theta. So v naught y is going to be v naught sine theta. Acceleration, again, is going to be due to gravity, and that's going to be pointing opposite to the velocity. So that's why it's negative. This is actually an important point to make. When a projectile gets to the top, it doesn't actually reach zero speed, right? It still has its horizontal velocity, which again doesn't change. But vertically, gravity has slowed it down until it reaches zero vertical speed. So what we can do is we can say v final in the y direction is 0. Okay, cool. Now that we got all these variables, we can plug this into a kinematic equation. This time we're going to use the equation that doesn't deal with time, okay? So the equation that doesn't deal with time, you can go back to your base formula sheet. You'll see it's going to be vf squared is equal to v naught squared plus 2a delta x. Highly recommend, if you haven't already memorized these kinematic formulas, to do so. They're very easy to memorize, and they make problem solving a lot faster. Okay, plugging in all the numbers into the equation. This will be 0, because v final is 0. And solving for delta x, well, technically this should be delta y, because it's my vertical heights. And so if I do that, I'm going to get negative v naught squared over 2a is equal to delta y. I'm going to swap out delta y with height max. So that's my maximum height. And that's going to be equal to negative v naught squared, which is really going to be v naught sine theta squared, all over 2 times the acceleration, which is negative g. Okay, so I don't want to forget the negative over here. So this negative and this negative will cancel out. Okay, cool. And so that's going to be the last equation here. And now that I'm actually looking at this, I realize that I didn't actually square that. So that should be squared right there. So I'm going to fix that on the formula sheet. So that's it for kinematics. Let's move on to dynamics. Now, when it comes to dynamics, these are everything that involves basically forces. So the first equation we're going to derive is let's actually go back to it. So the acceleration on a frictionless incline. So if you have anything on an incline, draw an FBD for it. Most force problems are going to be solved using FBDs and the Newton's second law. So that's just a framework to consider. So mg points down, the normal force points up. And again, this is a frictionless incline. So therefore, the only force that actually pulls this thing down and accelerates it down the ramp is this component of mg. Whenever we do inclines, the angle of the incline, so that is equal to this angle up top. And that's honestly something that you can just memorize. And so therefore, what component is this? This is going to be the opposite side. So that's going to be mg sine of theta. Okay, so mg sine of theta is what's my net force. So F net is equal to ma. So mg sine theta is my net force, and that's going to be equal to ma. The masses cancel out, so the acceleration on a frictionless incline will always be g sine theta. Okay, so again, this is actually a quick formula that you should really just be able to do in your head. Next up, we have the normal force. Okay, cool. So the normal force, this is actually very, very simple, but it's often a misinterpreted thing. So the normal force is going to be, on a flat surface at least, opposite to weight, yes. But the formal definition of normal force is going to be perpendicular to the surface. Normal means 90 degrees. When you're doing this, when you're doing these problems, and if you're on a flat surface and the object is not accelerating, then yes, the normal force is equal to mg. So N is equal to mg. However, what happens when the object actually starts to accelerate vertically? Well, we call this the normal force, aka the apparent weight that acts on an object. And so take a look here. Let's actually, for example, say that the object is accelerating downwards. So how would I show that? Well, if something is accelerating downwards, I need a net force downwards. So I'm going to draw my FBD such that I'm showing an overall force, a net force downwards. I'm going to go ahead and make an equation for that. That's going to be mg, so the bigger force minus the smaller force, mg minus n is equal to ma. I'm going to go ahead and solve for normal force here. Normal force is going to be equal to mg minus ma. And so what does this tell us? Well, looking at the equation, what it means is that mg is what we actually weigh. This is a real weight. As you can see, we're taking away something from our weight, which means that our normal force, or our apparent weight, which is again the force that we feel, is going to be smaller. So in other words, we're going to feel lighter as we're accelerating downwards. Okay, that's all that means. So here's our first equation for normal force. But what happens if you're accelerating upwards? So I'm going to draw something that's accelerating upwards. So normal force and mg. So that's if it's stationary. So I'm going to make normal force bigger this time, or attempt to make it look bigger. This time it's going to be n minus mg. So n is the bigger thing in this case, and that's equal to ma. So this time my normal force is going to be ma, or let's write it this way. Let's do mg plus ma. As we're accelerating upwards, the normal force is bigger, which means we feel heavier, hence why we're adding ma to our original weight, our real weight, I should say. And so therefore, a versatile formula that can work is that the normal force is simply our weight plus or minus ma, depending on which way we're going. Hence why that equation is N is mg plus or minus ma. Okay, so that was the apparent weight formula for an object that accelerates vertically. All right, let's take a look at the next one, which is the normal force on an incline. So this is going to be pretty straightforward as well, actually. So we already kind of sort of did this. So breaking this down into two pieces, we see that the normal force is simply equal to this component right here, right? So these two things have to be balanced. And this component right here is mg cosine theta, right? Because this is the angle, this is the angle, and so therefore that must be the cosine component of mg. And so mg cosine theta is simply equal to the normal force. Okay, that's it. The force of friction, okay, this is going to be the maximum force of friction, okay? And so the maximum force of friction comes due to the normal force. So friction is just mu times n. And so depending on the normal force we apply, that's going to be our maximum force of friction. So in the case of static friction, this is the maximum static friction. But sometimes you don't actually need all of this force, right? How much force do you need to keep it stationary? Well, just as much as this component right here. So as long as you have enough force to balance out this component, that's as much static friction as you need. This, again, is the maximum. So this is actually going to be actually in the base formulas. So in the base formula somewhere, I probably explained this already, but it says right here, the force of friction is either mu k times n, so this is kinetic friction. This can really only be one value, but static friction can be a range of values, and mu sn is the upper bound, which means that it can apply a maximum value of this, which is what we derived over here. Okay, moving on to the next derived formula. So this is where things start to get a little tricky. All right, now that you watched a little snippet of that derivation video, go ahead and download that equation sheet that I've mentioned with all the derived formulas, and just basically derive, practice doing the ones that I have on my page. And if you've already done all of them, look for other common scenarios that you can also derive and derive those. And then if you've done all that, go to UBQ, find some questions, and put your derivation skills to the test. All right, that's it for this video, guys. Hopefully that was helpful. If it was, please leave a like and a comment for me. That just lets me know that I did okay with my explanations. And if I did omit something that you feel like I should have included, please be sure to comment that below, so that way maybe other people can actually practice that. I'm not perfect, so I probably did miss a few things here and there. So again, I can use your suggestions for next year as I remake this video. All right, take care, guys.